let me take you back in time to a place without the wonders of the modern world. 500 years ago the earth was dark, a place of mystery and superstition. But then science changed everything. This series will tell the stories of the British scientists who changed the world. We have asked some of the great scientists and inventors of today to tell us about their heroes.
Now let's start her up.
It opened up a whole new world of the very small.
Heat was Thomson's big idea.
For me, Hunter is a true hero.
Exciting possibilities.
He made science in Britain really matter.
Britain has a tremendous scientific legacy that most people know little about. We want to set the record straight and put science back on the map.
The world is full of wonders, but they become more wonderful when science looks at them.
Our story began in the 17th century with a handful of men who unlocked the puzzle of gravity. The next generation took science out into the world. They harnessed steam to kickstart the Industrial Revolution. Today, we want to tell you about their heirs, 6 men of ambition, who between them would use science to light up the world. Science had come of age.
The 19th century was the time to think big. Big machinery, big enterprises, and big ideas about energy, evolution, and engineering. The stage was set, the show could begin.
Imagine you were alive in 1800 and someone had offered you a ride in one of the newfangled hydrogen balloons. You'd have seen a country full of farms and fields. There were no railways. A letter would be carried by horseback. By day, the new steam engines would thunder, but when the sun went down, the country went dark. But all that was about to change.
On a spring day in 1813, a young man, just 21, walked down Albemarle Street in London to start a new job here at the Royal Institution.
His name was Michael Faraday, and if one man switched on the lights of the world, it was him. This is his portrait, captured through the new medium of photography. He was in his 50s when this was taken, an acknowledged leader of British science. But it had taken struggle and genius to get there.
Faraday was born into a poor family. His father was a blacksmith, and the young Michael was apprenticed at an early age to a bookbinder. This brought him into contact with scientific papers, and he became fascinated by science, particularly by electricity.
In the early 19th century, it was a mystery. They saw it in the sky above their heads. They even had crude batteries. But no one knew what it was, how it worked, or how to harness it in enough quantity for it to be useful. Faraday was determined to change all that.
Faraday's genius was his use of physical experiments to explain his scientific mind. And on the 3rd of September 1821, he gathered together a few materials and made something that would have far-reaching effects. And this is my version of it. There's a bowl of mercury, a magnet in the center, and a copper rod connected by a wire to a battery. When I connect the wire, you'll see the copper rod rotating around the magnet. Now what's happening is that there are magnetic forces down the magnet and also magnetic forces down the copper rod, and one repels the other, and so you get rotary motion. Now it may not look like much, but this is the first electric motor.
What Faraday had done was make something extraordinary out of two things people took for granted. He had combined the chemical electrical current of the familiar battery with the powers of attraction and repulsion of the familiar magnet. The interaction of the magnet and the electricity created mechanical work in the form of the piece of wire spinning round and round. Faraday had shown us how to harness electricity to make a motor. Now what was really needed was a way of generating electricity without a battery. It took Faraday years to find one, but when he did, it looked simple.
Using just these, a magnet and a coil wrapped with wire, he was able to create magnetic induction, an electric current. As I move the magnet through the coil, I create an electric charge. In 1831, Faraday invented the first dynamo, and with it, changed our lives forever.
In his London workshop, Faraday had become the first person to harness the power of electricity, paving the way for turbines and power stations, cities with lighting and heating, powering everything from the TV you're watching to the life support machines monitoring human heartbeats. But it would take decades before Faraday's theoretical ideas would leave the laboratory and make an impact on the wider world.
One early application of Michael Faraday's work took place here at the Southforeland Lighthouse on the Kent coast.
The Southforeland Lighthouse had been built to provide a safe bearing for ships leaving or entering Dover, so they could avoid the Goodwin Sands 3 miles off.
Michael Faraday was asked to be an advisor to Trinity House, the body that supervised the country's lighthouses. He was convinced that electricity could be used to power the lamps, and he supervised the installation of an electromagnetic generator. In December 1858, Southforeland became the first lighthouse in the world to show an electric lamp.
Eventually, there was a chain of lighthouses around the country, beaming electric light, saving lives, and showing just what this great energy could do.
But it is a far cry from a generator that can power a single light to lighting up a whole city. And it would take the genius of other men to take Faraday's great discovery and find a way to make it power the world. In an era of big ideas, one idea towers above the others: evolution. It explains how we gradually came into being and how all living things are connected. One man is famous for this theory: Charles Darwin. But there is another man, always in history's shadow, who is also important. The Victorian naturalist, explorer and collector, Alfred Russel Wallace.
For me, Wallace deserves lasting admiration, not just because he had the intellect and imagination to think of the theory of evolution by natural selection independently of Charles Darwin, but because he showed such grace and gentlemanliness over the authorship of that great idea. He was a brave and original man. His life was adventurous and difficult, and he carved it out for himself without benefit of any social or financial advantage. This contrast in circumstances between the two men makes a compelling subplot to the story. Wallace, one of 3 brothers, was born in this house near Usk in South Wales. They didn't stay here long. The family were middle class, but Wallace's father, in a typical Victorian story, speculated unwisely, and the family's finances steadily crumbled. Charles Darwin, 14 years older than Wallace, came from a wealthy Shropshire family who had provided him with support and stability. Indeed, it was his connections that secured Darwin's place on the famous voyage of the Beagle that would prove so inspirational to him. By the time Darwin was returning to his comfortable home in Shrewsbury with his specimens, the 13-year-old Wallace was lodging with his brother, a builder. His education ended, his future uncertain. The young Wallace had to make a living. So a year later, he began work as a surveyor's apprentice. It was a job that would have an impact on his world. The outdoor life suited him. He learned to measure, to use a sextant, and he began to survey nature, deriving inspiration from Darwin's own writing. Wallace began to train himself as a naturalist. Following Darwin's advice in The Voyage of the Beagle, he began with plants, and he built up his own herbarium. A friend introduced him to the wonderful world of beetles. Like Darwin, he became a collector. He studied a treatise on the geography and classification of animals. He began to build up a picture of species within genera, within orders. He began to wonder about the differences between species and how they arise. These were exactly the questions that were perplexing the older Darwin. On his trip to the Galapagos, Darwin had noticed differences between species from one island to another. After his return, he began to wonder if these changes occurred over time, from generation to generation, so that from one common ancestor there were very many, very different descendants. But if this was so, why did these changes occur? At this time, many people still believed that the earth and all living things had been created by God in just 6 days. Darwin knew that to suggest otherwise was deeply controversial. He didn't publish. Meanwhile, Alfred Russel Wallace had his eyes set on the chance to do some original research of his own. Wallace was nursing a big idea. He knew that in Victorian England there was a growing market for specimens of insects and birds. Why shouldn't he become a collector on a grander, more adventurous scale, while at the same time pursuing his researches on the origin of species? He persuaded a fellow naturalist, Henry Bates, to join him. He saved all he could from his railway work. He read up on the fauna and flora of the Amazon. He collected equipment and letters of introduction. And on April the 26th, 1848, at the age of 25, Wallace, with Bates, set off from Liverpool for the Amazon rainforest. It would be many years and several dramas later before they would return.
While Wallace and Darwin were beginning to form theories about how we had all evolved, their contemporaries were starting to change the society they lived in. The era of country lanes and travel by coach and horses was over. The railway had arrived. Much of this was due to the work of one man, someone who really knew how to think big. Isambard Kingdom Brunel.
My hero and addicted to the impossible, Brunel wasn't just an engineering pioneer. He made quantum leaps into the unknown. He was brave and he was audacious. He was a compulsive risk-taker. Never accepted current thinking. Always wanted to find a better way.
Brunel's story begins when, as a young engineer, he travelled to Bristol, drawn by a competition to design a bridge over the River Avon. Only in his early 20s, Brunel slung a cable across this gorge, the first step in building the Clifton Suspension Bridge, the longest single-span bridge yet attempted. Edging across it in a basket, the rope snagged, and the fearless Brunel climbed onto the wire to free it, 200 feet above the ground. But this stunning bridge was by no means his greatest achievement. Evidence of Brunel's work is still all around us. From Paddington Station to tunnels through solid rock, Brunel's work exemplifies the ambition of the age. After completing the Great Western Railway from London to Bristol, he thought, why stop there? Why not build a great ship and extend the route to New York? They built and launched her in Bristol in 1837 and called her the Great Western.
On her maiden voyage in 1838, the Great Western reached New York in just 15 days. A triumph, but not enough for Brunel. Although seriously injured during a fire on board during sea trials, Brunel had an urge. Bigger, better, and faster. So in July 1839, he started work on this, the SS Great Britain. The speed of a ship is a function of the square root of the length times a constant of 1.34. So the longer the ship, the faster she goes. So Brunel built big, the biggest ship in the world.
And she needed the biggest engine in the world. "1,000 horsepower of steam-driven monster, designed by Brunel himself."
And this is my favorite bit, the propeller. Up until this point, ships had paddle wheels, efficient until you go in a stormy sea. I've knocked up some little models. As the ship rides the wave, the paddle wheel comes out of the water and the ship slews, causing horrendous loads on the drive mechanism. Whereas with the propeller, located low down at the stern, stays submerged, drives smoothly, and is far more efficient. So Brunel took the plunge and committed to propellers.
I love the way he investigated and refined. He set up a tug-of-war between the Rattler, driven by a propeller or screw, and the Alecto, which was a paddle ship. The Rattler won. He tested dozens of different propellers throughout the trial.
These are Brunel's own workbooks in his own hand, where he recorded the results of each test, different diameter, different pitch, and different shape. And over here, he's translated them into graph form, so you can compare one result with another. Now for me, this is the birth of research and development.
Experimenting, testing, refining. This was the start of modern engineering.
And this is what Brunel eventually came up with, a monster six-bladed propeller. It's made of iron and weighs 4 tons, and it's over 15 feet from tip to tip. It's only 5% less efficient than a modern-day propeller, and it propelled Britain in the mid-1800s into the age of transatlantic ocean travel.
The Great Britain was launched by Prince Albert in July 1843, the biggest and most technically advanced ship the world had ever seen. She was a triumph of Victorian engineering and sailed over 1 million miles across the world's oceans before eventually returning to her home here in Bristol. But Brunel had even greater schemes yet to come.
By the mid-19th century, there seemed no limit to Britain's ambition. So in 1851, Victorian Britain threw a party and invited the world. The Great Exhibition brought together the great scientists of the day. Brunel was on the committee which designed the building. Michael Faraday was in charge of the scientific displays. This was a celebration of a society built on steam power. And it was about to become more powerful still, thanks to the work of another young scientist. The Great Exhibition showed the world just how successful Victorian Britain was. This was a world built on steam power, but there were still questions. No one understood how heat and water could unleash such energy, until an ambitious Scotsman cracked the mystery. His name was William Thomson.
Thomson was born in Ulster, but he spent almost 50 years at the University of Glasgow as Professor of Natural Philosophy. He was a Presbyterian Victorian go-getter. He was clever, ambitious, and precocious. He enrolled at Glasgow University at the age of only 10, and he had a ferocious work ethic. As a student, he set himself a punishing schedule. He would get up at 5 and start reading. At 8:15, he'd go to lectures, read again, and then exercise until 4 in the afternoon when he'd go to chapel. He'd stay there till 7 and then read again until 8:15, finally going to bed at 9. Now, if he really stuck to that schedule, the man was more of a machine.
He realised that it wasn't a substance, which is what other people at the time thought, but a form of energy, and one that could be converted into mechanical work. He set it all down in the laws of thermodynamics, and these gave Victorian engineers a framework that meant that they could understand, design, and build better machines, and ones that wouldn't waste energy.
As a scientist, Thomson's interest in heat naturally included an interest in cold. His formulation of absolute zero became an essential scientific tool. And his ideas about heat exchange are used by almost every area of science. But Thomson was soon to become as famous for his inventions as for his scientific breakthroughs.
William Thomson formulated his famous temperature scale in 1848. In that same year, another of our geniuses was just setting out on his own great adventure. When Alfred Russel Wallace landed in South America, he had no inkling of the triumphs and disaster to follow.
Wallace embarked on a perilous series of collecting expeditions, recruiting local help as he went. He explored the Rio Negro, ranging as far as the Venezuelan border. He collected butterflies, birds, beetles, monkeys, even a small alligator, and a boa constrictor whose hissing resembled the sound of the steam escaping from a Great Western locomotive. He recorded all his specimens, including these fish from the Rio Negro. After 4 years, Wallace had collected a huge range of flora and fauna. Some monkeys and birds he'd take back alive. But he wasn't just collecting, he was thinking. What could explain the extraordinary diversity of nature? Why were there differences between creatures of the same species? By taking his specimens home to Britain and studying them at leisure, Wallace hoped to find some answers. But he had no idea what lay ahead. Three weeks out, tragedy struck. The ship caught fire. Wallace was able to save only a few drawings and a couple of shirts before taking to a lifeboat. From there, he had to watch his living monkeys and parrots perish in the flames. All the fruits of his labours, all his other drawings, his journals, his specimens went down with the ship. Wallace himself spent 10 days in an open boat before being rescued. No wonder he wrote to a friend, "You will see that I have some need of philosophic resignation to bear my fate with patience and equanimity." Meanwhile, Charles Darwin was safely tucked away at Down House in the middle of an 8-year study of barnacles, a study that helped cement his reputation. His ideas were developing, but still he didn't publish. Wallace had to start again. He returned to England to recover and raise more funds. He hadn't stopped thinking about the differences between species and what might cause them. A year and a half later, he was able to set off on a second trip, this time to Asia, the Malay archipelago. And it was here he had his breakthrough moment. One day, feverish with malaria in his lonely hut, inspiration came to him. Suddenly, as he later recalled it, he remembered reading Malthus's essay on population, with its emphasis on overpopulation and the checks that must inevitably result: war, famine, disease. Wallace realized that these checks must also apply in nature. Here, he had a mechanism to drive the modification of species. In the struggle for existence, and Wallace actually used that phrase, those individuals best equipped with strength, cunning, speed, would pass on their characteristics to future generations, and the species would improve. Within 2 hours, Wallace had sketched out his theory. In the following 2 nights, he wrote it out fully, and then he sent it by the very next post to Charles Darwin. When Darwin received Wallace's letter, he reacted with a mixture of amazement and despair. It was as though he were reading his own theory, which he hadn't, of course, yet published. What should he do? Should he cede priority to Wallace, as honour seemed to dictate, or should he claim it for himself and risk a lengthy and unpleasant priority dispute? To make matters worse, Darwin's baby son was dangerously ill with scarlet fever and thought unlikely to live. In desperation, Darwin turned to his friends Hooker and Lyell for advice. And Lyell came up with a solution. Why not present the two theories together? The occasion chosen was a meeting of the Linnean Society here in what's now the Royal Academy in July 1858. Neither Wallace nor Darwin attended. Wallace was still in Indonesia, and Darwin was burying his son. This was the first time that the world would be told how life on Earth came to be. The papers were read in strict chronological order. First, Darwin's paper of 1844, then his 1857 letter to Asa Gray, and finally Wallace's 1858 paper on the tendency of varieties to depart indefinitely from the original type. For such a momentous event, it fell as a bit of a damp squib. A friend reported to Darwin that the interest was intense, but the subject was too novel and too ominous for the old school to enter the lists without armouring. Even the president of the Linnean Society was one of those underwhelmed. In his end-of-year report, he said that 1858 has not been marked by any of those striking discoveries which at once, so to speak, revolutionized the department of science on which they bear. When Wallace heard about the readings, he was delighted. "I not only approved," he wrote to his mother, "but felt that they had done me more honor and credit than I deserved." Wallace never showed the slightest bit of resentment or jealousy of Darwin. He felt that his contribution couldn't compare with the authority and wisdom of Darwin's Origin of Species, and he was thankful that he had been instrumental in spurring Darwin into writing it. Wallace even coined the word Darwinism and described himself as more Darwinian than Darwin.
Darwin and Wallace were both men of science, more concerned with truth and commerce. But this was an era when science thought it could conquer the world. Faraday's electricity was paving the way. A new invention used electrical impulses to send messages over short distances. But it would take the ambition of William Thomson to unlock the global potential of this new technology.
When Thomson wasn't lecturing, he was in his lab, getting the help of students to experiment with telegraphy. That's using electricity to send messages over distance. It was the first real commercial application of Faraday's theoretical work.
The idea of telegraphy is that you translate messages into electrical impulses which can be sent down a wire and reconstituted at the other end. Today, we do this every time we speak on a landline, but then it was revolutionary.
By the 1850s, telegraph networks were rapidly spreading across Britain, continental Europe and America. But there was still one great unconquered territory, the ocean.
So Thomson took on an idea of real ambition: to run a wire under the Atlantic and connect Britain and America. The difficulties were immense. How to design the cable, how to manufacture it, how to lay it securely on the ocean bed. The combination of theoretical and practical challenges appealed strongly to him.
In 1857, Thomson joined the first expedition. But after only a few hundred miles, the cable broke. The next year, they tried again, this time successfully. But after only a month, the cable failed completely.
Thomson set to work on the problem. It seemed that the cable was just too thin for the signal to get through reliably. But there was one man he knew could help him. Michael Faraday, the guru of electricity. And by using his research, Thomson developed a cable which worked better, one with thicker copper wire and more insulation. He also invented a new piece of kit vital to receiving the signals.
Now, this is the galvanometer that Thomson built, and it's an incredibly sensitive instrument that can measure tiny fluctuations in electric current. Now, that really mattered because it was those tiny changes in current that were carrying messages in the cables under the Atlantic. So, to detect the messages, you would send the current through the galvanometer, and there's a tiny little mirror in there with magnets on it, and it would move according to the current, just a tiny amount. You'd bounce a light in, and the amount that the light moved when it came back out told you really accurately just how much current was going through.
Now what Thomson needed was a ship big enough and strong enough to lay the cable. And for that, he would turn to the work of one of our other geniuses.
The Great Britain hadn't been enough for Isambard Kingdom Brunel. He was consumed with the idea of an even greater ship. First called the Leviathan, then the Great Eastern. But to Brunel, she was always known as the Great Babe.
No one asked Brunel to build her. She was his own gigantic idea, a double-hulled, steam-propelled ship so huge that she could carry enough coal to sail to Australia and back without refueling. At 700 feet, she would be twice the size of the Great Britain and would carry 4,000 passengers.
Brunel persuaded the Eastern Steam Navigation Company to initially bankroll the project. But Brunel committed himself heavily, both personally and financially, and the ship would consume the last 7 years of his life.
The construction was recorded in this remarkable set of photographs. But from the start it was troubled. On the Great Eastern's first launch attempt, a labourer was caught by the handle of a winch and was mangled to death in front of a crowd of horrified spectators.
This is the last photograph of Brunel, taken aboard the Great Eastern in September 1859. You can see he's unwell, stress doubtless taking its toll. 2 hours later, he collapsed on board and was unable to make the maiden voyage.
On that voyage, bad luck continued to dog Brunel's great babe. Off Dungeness, an explosion ripped out the forward funnel, killing 5 stokers and injuring several others.
The news was conveyed to Brunel as he lay on his sickbed, anxiously waiting to hear of his great babe. 7 days later, he died.
But that wasn't the end of the Great Eastern. The prize for the successful transatlantic cable was still up for grabs, and Brunel's great babe, with her huge holds and manoeuvrability, would win it for the Atlantic Telegraph Company and for William Thomson.
Soon, underwater telegraph cables would span the world, enabling communication between Britain's far-flung imperial possessions. Previously, it would have taken long, hard weeks for a message to reach a foreign country. Now, it could be communicated in moments. This had far-reaching effects for catching criminals, changing businesses, and speeding up diplomacy. William Thomson's work on the transatlantic cable brought him a knighthood and more. He became Lord Kelvin, but more was still to come. Since Faraday's discovery of how to generate electricity, no one had yet managed to construct a generator big enough to power anything larger than a house. But in the 1890s, William Thomson was asked to help with a scheme to make power out of the Niagara Falls. He relished the task. And in 1895, the first hydroelectric power station in the world was opened, using Faraday's discovery, William Thomson's talent, and a large dollop of 19th century enterprise. And in 1902, Thomson was delighted to open Britain's first industrial power station. Now, at last, the lights could really go on.
60 years earlier, Michael Faraday had discovered how to make and use electricity. Since then, men like Thomson had used it to light up the world and led nation speak unto nation. But one last Victorian genius remained, who may be greater than them all. There is a famous story that Albert Einstein had 3 portraits on his study wall at Princeton. One was Sir Isaac Newton, the next, Michael Faraday. The third is a personal hero of mine, the physicist's physicist, and the man whose work revolutionized global communications. James Clerk Maxwell.
For a man whose discoveries in electromagnetism gave us the mobile phone, and TV, radio and radar, whose work on vision allowed us to record the world in colour, the name of James Clerk Maxwell is remarkably little known. In fact, outside the world of science, it's a bit, well, neglected.
This is Glen Lair, the house in Galloway where Maxwell, the son of a modest Scottish landowner, spent his childhood and much of his adult life.
I remember this wonderful moment as an undergraduate student learning about electromagnetic theory. The lecturer had just scribbled a set of equations on the board called Maxwell's equations, and he'd worked through some complicated maths to arrive at one of the most fundamental quantities in nature, the speed of light. It was that realization, something Maxwell had discovered, that light, electricity and magnetism are all connected in a fundamental way. I remember feeling slightly embarrassed by my geeky excitement, but the maths was beautiful.
But these days, I'm also interested in the man behind the maths. Apparently, he was a very curious child. His constant refrain was, "What's the go of that?" Meaning, how does that work? From early on, his imagination seemed to penetrate beyond objects, to the underlying structures beneath.
As a 3-year-old, he was apparently shown a stone and told that it was the colour blue. He replied, "Aye, but how do you know it's blue?"
His curiosity continued throughout his life. He was fascinated by vision, with eyes. He particularly loved dog's eyes, and even invented a special instrument to study them.
He invented the fisheye lens after apparently becoming fascinated by the structure of the eye of the kipper he was going to have for breakfast.
As a student at Cambridge, Maxwell became preoccupied with how to mix colours together to reconstitute white light.
After a lot of experimentation, Maxwell worked out that he needed just 3 colours, red, green and blue, to synthesize normal white light. His theory of colour vision gave the world a recipe for combining colours and is the basis for the colour picture you're looking at now.
By the 1860s, Maxwell was an established physicist and mathematician. He was very friendly with William Thomson, friendly enough to tease him over his problems with the transatlantic cable. Under the sea, he wrote, no little signals are coming to me. But he reserved his greatest admiration for the work of Michael Faraday, now an old man. And it was through examining Faraday's great discovery of electromagnetism that Maxwell would make his own discovery and change the world forever.
Maxwell's project was nothing less than to develop a theory that described all the effects of electromagnetism, including light, because Maxwell believed that light itself was a form of electromagnetic energy. Now, Maxwell used a lot of the data coming from Faraday's work, but whereas Faraday did the experiments, Maxwell did the maths.
These astonishing equations wrap up electricity, magnetism and light into one perfect system. Just as Newton 200 years earlier had unlocked the secrets of gravity, Maxwell had found the keys to electromagnetism, and with them, the world is our oyster.
Working sometimes here at Glenlair and sometimes down at King's College London, Maxwell conjured up his set of 4 beautiful equations. He took information about how electric and magnetic fields behave, added in his new ideas about light, and then translated everything into mathematical symbols. He then manipulated these symbols to come up with a set of mathematical results which not only explained how things behave now, but predicted new effects and new phenomena which could and would be discovered in the real world.
Maxwell died young at 48, but only 8 years after his death, the first of the predictions from his theory was realized when a German physicist produced and detected radio waves. Soon after, the Italian engineer Marconi began the first radio transmissions, sending messages through the air without wires. Appropriately, Marconi had set up his receiving station at South Foreland Lighthouse, where Faraday had first generated electricity for the light. There, the first ship-to-shore transmission was received, and the first international radio message was sent.
The radio waves flowing out of Maxwell's equations would accelerate the explosion in communications that had begun with the electric telegraph and would shape the coming century, shrinking our world even further, creating the global village. People at the time, and that included other scientists like Kelvin and Faraday, didn't really understand Maxwell's ideas. It was a bit like Einstein popping up in the 1860s talking about relativity. And therein lies another reason why James Clerk Maxwell is so important. He created a new language for science, a new methodology for the theoretical physicists of the coming century. Rather than working with coils and magnets, they would work with mathematical symbols and use them to explore new ideas, make discoveries, come up with new theories that they could then test in the real world. So Maxwell didn't just give us the mobile phone. He gave us a new way of investigating the world.
In just 80 years, science had changed the face of Britain and the world. Railway lines, power stations, vast cities, teeming factories. A place on the brink of radio and television. A place where the radical theory of evolution had helped to open people's minds to the truly extraordinary wonder of nature. None of this would have been possible without the work of 6 great British scientists. Faraday, Darwin, Wallace, Brunel, Thomson, and Maxwell created the world we know today.
Next time, in the 20th century, science would bring great benefits and great horrors. And as Britain lay beleaguered and bombarded, it was the scientists and engineers who would find the skills, machines, and intelligence to save her.
The agonizing story and a race against time to halt the growth and save the life of one of the tallest women on Earth. I'm turning into a giant, a Body Shock special next, while I'm more for an alternative view of the World Cup. True stories, the power of the game next.